frequency of free longitudinal vibration. So we are going to consider a spring mass system. Okay, so initially we consider the spring alone. Okay, a spring is there, it has a stiffness of K, and it is the case 1. And the case 2, we included a mass, okay, so which is attached to the spring, which is having a stiffness of K. Okay, so once the mass is attached to the spring, so what has happened here is it has been displaced to some distance. Okay, so that distance is delta. Okay, it is delta. Yes, okay. So after adding the mass here, mass is m, so the spring has been displaced to certain distance that we have considered that as a del. Okay, and in the case 3, so what has happened here is, here I'm going to induce vibration on that. Okay, so that is longitudinal vibration. So I'm just going to move the mass in the downwards direction to induce the vibration on the system. Okay, so what has happened is this spring has even displaced further from this position. Okay, so here we can take this position as equilibrium position. Okay, this position, and here again it has moved to another distance, that is here the distance the spring has moved is x. So that means I have moved the entire system in the downwards direction, the mass, to induce the vibration. Okay, then I am going to allow it to vibrate on its own. So that is why we call that as free longitudinal vibration. Okay, so once I release the system, it is going to be here, and then it is going to move in the upward direction. Okay, then again it's going to move downwards direction, like that the motion is happening continuously. Okay, as long as all the energy uh, are lost. So once all the energy is lost, then it will come back to equilibrium position. Okay, so by using these three conditions, we are going to find the frequency of the free longitudinal vibration. Okay, so for this,
And
for the case 2, so now I'm going to construct the free body diagram for the case 2. Okay, so now here we know that it has got a mass. Okay, so we're going to consider the free body diagram for the mass. So it has a weight. Okay, so we know that weight is equal to m into g. Okay, and here is a force. So this force is called spring force. Okay, it is spring force. Okay, because of the spring, it just tend to pull the entire mass in the upward direction, whereas this weight tend to pull the mass in the downwards direction due to gravity. Okay, so this system, it is a static system because it is in equilibrium condition. Okay, so the mass is acting in the downwards direction, creates weight, and the spring force is pulling the entire system in the upward direction. Okay, so now I'm just going to explain you how to find out the spring force, because so here we know that the stiffness unit is Newton per meter. Okay, so otherwise we can say that stiffness is, okay, so stiffness is force divided by deflection. Okay, so now we need to find out this force. Okay, this force is called spring force. Okay, so if you want to know the spring force, what do you have to do? You need to multiply the stiffness with deflection. Okay, so now to find out the spring force, I have to multiply stiffness with the deflection. Okay, so here what is the stiffness? That is K, and what is the deflection? It is del. Okay, so now the free body diagram for this system is completed. So according to equilibrium condition, so what we can do is So here what is that? mg is equal to k del. So this is what the thing that what we have got from the case 2, the free body diagram of the case 2. So here it is in equilibrium condition. So that means the force which is acting in the downwards direction is equal to upward direction. So how to find out the spring force? We have to calculate it from the stiffness formula. Stiffness is force divided by deflection. So spring force is stiffness of the spring times the deflection that it has undergone because of the force which is applied. Okay, so now we've got an equation, that is, or the condition, mg is equal to k del. Okay, so now I'm just going to construct the free body diagram for the case 3. Okay, so here, unlike the previous case, it is in motion. Okay, so because initially what I have done is I have pulled the entire system in the downwards direction, so the motion happens in the downwards direction. So here we are going to apply the D'Alembert's principle. Okay, by using D'Alembert's principle, we can consider this dynamic system as a static system. So we all know that. Okay, what is D'Alembert's principle? So if you include inertia forces in the system, then we can consider as a static system. Okay, that is what the D'Alembert's principle is. Okay, so while uh, constructing the free body diagram for the case 3, so I'm just going to consider the free body diagram for the mass. Okay, so here is the mass. So it is obviously it is going to be downwards direction, that is mass, that we all know that. Okay, and we have to add the spring force, but here it has got an additional deflection. Okay, so initially it has got deflection del, and then once I pulled it in the downwards direction, it has got an additional deflection of x. So here, how to write the spring force magnitude? So k times del plus x. So deflection, we have to put it here. But deflection, the entire deflection is the summation of del and the x. So here it is k times del plus x. Okay, so then it is in motion. Okay, it is not a static condition. So we, according to D'Alembert's principle, we have to consider the inertia forces. So what is inertia force? According to Newton's second law, F is equal to ma, and this is what the inertia force. So inertia force is mass times acceleration. Okay, and we must remember the thing, that is, the inertia force is exactly acting opposite to the direction of the motion. So here motion is acting in the downwards direction, so the inertia force is acting in the upward direction, that is m into a. Okay, m into a. Okay, so m is the mass and a is the acceleration of the system. Okay, in other words, we can just write like this. Okay, what is that? M into d square x by dt square. So instead of a, I can put uh, d square x by dt square. So now the dynamic system becomes a static system because we have applied D'Alembert's principle here. That means we have considered the inertia forces in the system, so it becomes static. So now we are going to apply the equilibrium condition for the case 3. Okay, so we have mentioned all the forces which are acting in the system, including inertia force. So now we are going to apply the equilibrium condition. So that means the net force which is acting along vertical direction is equal to 0. Since there is no horizontal forces, we have to take net forces which are acting in the vertical direction is equal to 0. So, okay, so now we will write the equation. Okay, so for this condition, so what you have to do is, so upward force, that is m d square x by dt square plus k del plus x. So this term, okay, so I have included these two terms, and this one is minus, that is minus mg is equal to 0. Okay, So this is equation number 2. Okay, so in this equation, initially what we are going to do is we are just going to replace this mg by k del, because we know that what is mg is k del. Okay, so I'm going to substitute mg value in equation number 2. So it becomes m d square x by dt square, and I'm just going to expand this term also, that is k del plus kx. Okay, and here it is minus, what is that, mg is equal to k del, okay, is equal to 0. So now these two things gets cancelled. So the final equation becomes m d square x by dt square plus kx is equal to 0. Okay, so now we have to write this equation. And in my previous lecture we have seen how to derive the equation of motion, and the equation of motion is, what is that, that is d square x by dt square plus omega square x is equal to 0. So this is what the equation. Okay, so now I'm just going to compare this equation, that is equation number 3, with the equation of motion. So that what I'm going to do is I'm just going to divide this equation number 3 by m. So what I'm going to do m, so that I can relate these two equation. Okay, so d square x by dt square, because m is going to get cancelled, plus k by m x is equal to 0. Okay, so now I am going to compare these two equations, so equation number 4 and equation of motion. Okay, so from that, so you can easily understand that here d square x by dt square and d square x by dt square are common, and only the difference is here omega square is there, here k by m is there. Okay, so and from that, by comparing equation 4 and equation of motion, so what we can do is we can write omega square is equal to k by m. Okay, and so we can write omega is equal to root of k by m radian per second. Okay, the unit for omega is, it is a radian per second. It is a circular natural frequency. It is circular natural frequency. Okay, so instead of omega I'm just putting, because it's natural frequency, I'm just adding omega n, which is equal to root of k. Find out the f1 value. Okay, this is a frequency, okay, in hertz. Okay, so for that, okay, so what is natural frequency, f1, which is equal to, so I have to divide this term by 2 pi. Okay, and now the equation becomes f1 is 1 by 2 pi, so omega n is root of k by m. It is cycle per second, or otherwise we can represent that it is in hertz. Okay, so this is the frequency of longitudinal vibration. So it is, f1 is 1 by 2 pi root of k by m. Okay,